Hello, hello. Okay, so I have no questions from you guys yet. So I'm gonna keep working on my homework answer key until you guys ask something. Ooh, exciting. Yeah, these are oddly complicated for how simple the topic was. How do I solve all the things? Just Q. Q is the answer. So it doesn't have to be specific questions. It could be like, let's do an example of, I don't know, using heats of formation, or, hey, I'm stuck on number 76 on the homework, whatever it happens to be. I am happy to answer those. But without questions, I have nothing to answer. Molarity and thermochem equations. All right, nice and vague. Okay, so let me just go and make a new one. Okay. Okay, so examples of molarity and thermochem equations. All right, let's find a book. Okay. Not our chemistry textbook, but another one I happen to have. Let's see if we can't find something in here that will work out nicely. So thermochemistry starts on page 208 in this book. Let's look to some questions. Okay. Okay, let's see. What, I mean, yeah, of course. These might take too long to write. You know what, let's just make one up. Okay, forget it. Okay. Okay, so let's say I am going to take plus some sulfuric acid. Let me look up oxide and sulfuric acid. Okay. Cool. Delta H for this reaction is negative 57 kilojoules per mole. Okay, given to us, yes? So that's overall reaction, right? Let's see what will the temperature of the water be after the reaction. As always, we assume no. Okay, so we can do 66 after. Okay, so yeah, this will work. Okay. Cool. So we have sodium hydroxide and sulfuric acid reacting together. We're given how much enthalpy change is related. Okay, Kevin, we can look at that also. Is related to this reaction. And we are asked to find the temperature of the water after the reaction. So what exactly are we looking for here? What? Oh, I guess we have to say where it starts, right? 18.2 degrees Celsius. Fine, whatever. Okay. Yeah, now we have enough to answer this. So, what the heck is this question asking us to do? So, we're looking for a temperature, right? So after all of this work, we should get temperature. That's what we're looking for. And so if we look at all of the stuff given to us in this problem, yeah, I like that idea, Shane. That's a good way to start. So Shane has said we're going to find the moles of product. I agree that would definitely be a good idea to do. What are we going to do with the moles of product, do you think? Oh man, I made this tough for you, didn't I? Oh well. Indeed. And what does that give us? Yeah, it gives us the joules, right? And so, with those joules, what do you think we're going to do after that? So that's going to be joules from the reaction, right? However, this question is asking us for temperature of the water. The water is not the reaction, right? The water is the surroundings, yes? Oh my goodness. Let's also assume we're going to assume that the water is 50 grams. Okay, cool. So it looks like we kind of have some idea of what the heck we're doing. So complex problem we've got here. Again, this would be too long to be an exam question, but it's good practices because this is going to hit a lot of points. So it's a good problem to do. So Shane has said we should figure out the moles of the reaction. I agree. So, of course, in order to do that, we should probably have a chemical equation, right? And I'll be nice, I'll balance it for you, but this is an easy one to balance anyway. That's a 4, by the way. Okay, so for this, we know we have 10 grams of that guy. We have 50 mLs of 0.5 molar sulfuric acid. And we also have a delta H, right? Negative 57. Right away, is this reaction exo or endothermic? It's exothermic, right? We have a negative delta H. Awesome. That's good. So we are expecting the temperature of the solution to rise, right? it's gonna, because the reaction is gonna give off heat, so that heat will be absorbed by the water, and therefore its temperature will go up. So one thing to keep in mind is that that's one way to kind of just double check your answer. Is if you're expecting it to be exothermic, then make sure your temperature is going up. That'll help you remember the signs. So it looks like we have a stoichiometry problem here, and it looks like we have two reactants. So yeah, exactly, we're gonna have to do limiting reactant here. How annoying. I think it's 40 grams, yeah, for 1 mole. So this is how I would set up this particular one. Notice we have a 2 here. Where did this 2 come from? It's a reaction coefficient, exactly. So that's where that has come in. And so for the other one, we remember that molarity is moles per liter, right? So I'm going to just convert it to liters in my head. Again, that should be something that you should be able to do by now. Just divide by 1,000 to go from milliliters to liters. Okay. So, and since our coefficient in the reaction is 1 for sulfuric acid, we'll just have a 1 on the bottom. All right, Kevin, do your thing. I predict that sulfuric acid will be our limiting reactant, but let's find out. Don't forget, by the way, this is due Saturday, not Sunday. Okay, cool. And what about for... I'll do it real quick. So we have 0.25 divided by 2 times 57. It's going to be negative 7.13 kilojoules. Okay, so we're going to choose this one, of course. Always the smaller one. We can ignore the negative for like terms of like which one's smaller. We always look at like magnitude. So this tells us that this reaction is negative 1.4 kilojoules. Sounds good. I like it. Oh, I see. Correcting me. Oh, well done. Okay. Very well. But there was never a third sig fig there. I only see 2 as I've written it, so very, very good. Okay, so now what? The heck do we do now? We have our Q for the reaction that we got from delta H, right? We used delta H in our unit conversion here to figure out how much energy is going to be released. What's next? What do we do with this number? I like it, but you're one step ahead of us, Kevin. We have one thing to do first. This is heat of the reaction, right? The water is not our reaction. So what are we going to do? We will use the specific heat after, but we can't just say... Can't do that. Why? Yeah. That's right. We have to understand that this tells us that the Q of the water, the solution, is going to be positive 1.4 kilojoules. Remember, the reaction and surroundings have opposite signs. So we're going to see that it's actually 1.4 kilojoules, positive 1.4 kilojoules equals MC delta T. Yes, very, very good. And that's awesome that you got that one, because I know that was confusing for you. So that's awesome. Okay, so convert to joules. Okay, I like that idea. We could do that, sure. That'll be okay. I hope everyone's okay with me doing like kilo and milli stuff just automatically. It's should be kind of easy to do those, so review your metric stuff otherwise. Okay, so let's look at what we have here. We have a mass, we have a specific heat, we have, remembering that delta T is these two. We have a T initial, right? And we're actually looking for, yeah, exactly. We're looking for temperature final. This is what our question is asking us to find, the final temperature. So, if we plug all this fun stuff in, what temperature were we starting at again? 18.2, okay. At this point, it's calculation. So we would do temperature final is equal to 1400 joules over 50 grams. Plus 18.2 degrees Celsius. Again, this algebra should not be what holds you back in this course. Okay, our units, of course, should all cancel out except for degrees Celsius. Grams cancel, joules cancel. Remember, 1 over degrees Celsius is just regular degrees Celsius. It'll work out, don't worry. So it looks like it's going to be about 7 plus. Yeah, that looks about right. I like that. And so according to Kevin, we have gotten 24.9 degrees Celsius. And so that is how we would do that. So a lot of stuff, we have done a lot of stuff in this particular problem. So to solve this one. So, like if this were a written test, like that was free response, this would be, I think, a really awesome question to give you guys, because it tackles so many different points, and with that I could give you partial credit for ones you get right, and, you know, but since it's like multiple choice, it's not as easy to do that. So questions will have to be easier, or shorter at least. So that being said, let's go ahead and take a look. Let's just see what we did. So, all this fun stuff in our problem. So, we used stoichiometry with these two, using our delta H reaction. We used our MCAT formula. We also used our reaction versus solution, converting between the two, just their opposite signs. And so we've used quite a few things in this one problem alone. So we should all be happy for all the work we just did. Does anybody have any questions on like particular bits of this problem? Like why we would do this, why we did this thing, why we plugged this in, anything like that? By the way, if you did not flip your sign for the understanding Q reaction for surroundings as the opposite, you would end up with a temperature that was lower than what you started with. And that is one way you would know, wait a second, this was an exothermic reaction. It should have gotten hotter. Like, why is it getting colder? That tells you probably had a sign error somewhere in there. Yep, it's complicated. Lots of stuff. Aside from literally everything. When all else fails in chemistry, understand everything is unit conversions pretty much. We're just converting units the whole time. In some cases, we're using formulas to do it. Most of the time, we're just using the dimensional analysis, unit conversions. But essentially, we're just converting these quantities here into energy. Just unit conversion. Do you mean as kilojoules? Oh, you mean temperature for reaction. I see. Yeah, you would then use Q reaction. But again, reactions aren't really something physical, so we can't really measure them directly. But yeah, if some hypothetical thing were to ask you temperature of reaction, you would use the negative number, for sure. Yeah. So if you were theoretically calculating something that, for whatever reason, I asked you to do, you would leave the sign as negative. You would not flip it. You are correct. Okay, so anyways, yeah, so this stuff does seem quite complicated, but it's there's only a few things that are like kind of new in this chapter. So the stuff with the stoichiometry is very similar. I mean, we've done stoichiometry for pretty much the whole semester, so thankfully we're not really adding too much to that. I mean, we're throwing in delta H reaction, but that's kind of the only thing that's new there. And then after that, it's just some formulas. So, yeah, the hard part is kind of knowing which formula to use when, as always, anytime you have formulas. But sometimes, like, something that can help is you just kind of have to step back and think, okay, what are the components of this problem I know? And what am I trying to find? And then, yeah, I totally know. There's a lot of formulas, and it's like they all have Q's in them, and it's like, great. For sure. But really, it's sometimes just taking a minute to think, okay, how do I go from A to B in this? And of course, sometimes it might be like 5 steps to go from A to B, but I know on a test, unfortunately, there's time limitations that suck and are annoying. But I just wanted to kind of reassure you that while this stuff is, yes, there's a lot of things going on here, none of it itself is necessarily that hard. It's just kind of figuring out what to use when, and that just comes from practice. Yeah, exactly. Of course, yeah, I know, time sucks. So, yeah, I know. One example without mass. You mean like when we use a bomb calorimeter? So this would be something we're using coffee cup. Yeah, of course we can do a word problem. Okay, I can do both of yours at once. So one without mass and one that is a word problem. Okay. Of course, if anybody still has questions on this particular one, go ahead and throw them out. We'll see. Okay, a word problem using a bomb calorimeter. We also had some homework problems that we wanted to go over. Let me see if any of those would be appropriate for this. Let me find my book. If I remember correctly, someone had asked for number 66. So let's have a look. 66. Please be a bomb calorimeter. Oh no, it's a Hess's Law problem. Okay. Okay, fine. Away with this. Okay. Taking place in a bomb calorimeter. Are these usually given in kilojoules? Yeah, good enough. Okay. Wait. I have to just make sure our units are kind of reasonable. So bomb calorimeters, let's see. Total heat capacity. These are all asking for total heat capacity. Okay, they are given it in kilojoules. That's good. Okay. A temperature, the hold on. I'm trying to think of a reaction that would fit this. These are like, I want actual reactions. Give me 1 second while I find something that is endothermic. Oh, of course. Blah blah blah. Temperature decreases by 6.4 after reacting 49.6 grams of carbon dioxide. Yeah, this will work. We're going to do some photosynthesis here. Okay. Oh. Okay, let me move this up a little bit so we can see the whole question at once. Oh, that is so cool. Okay. Boom, question. Here we go. Word problem. Doesn't have mass. I assume you meant mass for the, like, calorimeter. Like, you'll always have to have a mass of something to find the moles. So I could just give you moles, actually, but yeah, fine. There. Okay, here. Now it's moles. Okay, so no mass this time. And it is a word problem. So walk me through it. One good thing to do about word problems is pick out your numbers. Like there's a bunch of numbers in this particular problem. One good thing to do is to just kind of write out what's what. So we know we have the first number that we're given is the heat capacity of our calorimeter, which is given to us as 8.2 kilojoules per gram degree Celsius. And we have a temperature decrease of 16.4 degrees. So what does that mean? If we were to put that in terms of a variable we're familiar with, what would that look like? After this, we'll do number 66 and then Kevin's question about whatever question he had. Just to get through that. Oh my gosh, I'm getting so popular. We've been bombed 2 days in a row. How exciting. As always, please do not click those links. Obvious spam. Though I guess this is more directed at me than it is at you. Yeah, no worries. Yeah. I was hoping if I didn't choose to become... Yeah, sorry. I don't have to keep rambling. Okay, so notice here, it says it decreased by... Okay, energy map thing, yeah. So, yeah, exactly, Shane, perfect. So delta T is negative 16.4. Notice because it says decreases. So that means it went down. So our temperature got colder. Alrighty. So, oh, I guess I haven't really asked you what to do. Sorry. I guess I should give you an actual question. Sorry. I've just given you a bunch of random numbers with no question actually being asked. Shane, you are correct for a coffee cup calorimeter. A bomb calorimeter does not have mass as part of it, because total heat capacity includes the mass already. Because the bomb calorimeter is just counted as one thing. So we don't have like actual water that we have a volume of. We just throw this thing in the bomb and watch the bomb heat up. So that's something we noticed as well. So that's one way we know we're going to use bomb calorimetry. So we have two formulas, right? For Q, we have that one, and we have this one. Let's see. Yeah. So we're technically, yeah, exactly. So technically these are different Qs. But really, who cares? We don't care about that. That's just going to confuse you more. But what we're looking at here is... oh, yeah, we have to have a negative on this because it's... well... Kevin, what I'm going to do... Did I give you the equation with the negative already in it? Did I give you Q reactions equation for that? Okay, then in case... Okay, then I'll keep it. I'll be consistent. So this is the difference, Shane. We have kind of two different things that we're looking at here. This one is the coffee cup, which is constant pressure, where we have some water in the coffee cup, and that amount of water will be varied, and that's why we have the M there. And so that's why we need the M here. The bomb calorimeter is just kind of one big old contraption that has a fixed amount of water in it. So because the water doesn't change between uses of that calorimeter, it's just easy for us to just combine them in one thing with as C calorimeter. And so this is the bomb here. And then, so this is constant volume. And this is the amount of water is fixed. So M is included in C cal. Okay? Cool. So these are kind of the two reactions that we have, or two equations that we have that we could deal with heat capacities. But in this case, we're using the bomb, so we want to use the reaction on the right. Does that make sense, Shane? Cool. Okay, so let's go ahead and plug in our numbers. So we are given the heat capacity is 8.62 kilojoules per degree Celsius, and delta T was negative 16.4. Notice, as always, we have units that cancel out. Kevin, what's our answer? Yes. If we want, we could look at the Q of the bomb, but who cares about the Q of the bomb? We care about the reaction. And I mean, if it helps, for the coffee cup, it's always Q solution. If you want, you could make it Q reaction by just throwing a negative sign in front of it. That would work. Totally okay. Awesome. So Q reaction is positive. That's endothermic, right? Looking at that, does that agree with kind of the information we were given? Yeah, it makes sense, right? We've decreased the temperature. So the surroundings have lost temperature, which means that the reaction has absorbed heat. So again, we always want to kind of just always double check to make sure that we're working out. Well, that's good. I'm glad this makes sense, but that capital "so" makes me worry. We're not done yet, Tyler. Don't worry. Shane is on the right track. So the last piece of information, we are given that we have 1.62 mole of carbon dioxide that's being reacted. And we're being told that by that has given us 141 kilojoules of energy. Right? So, yeah, you're absolutely right. Q reaction equals delta H. And we're trying to find delta H reaction. So remember, delta H reaction is basically just 1 mole, right? So how are we going to make this so that it's 1 mole? So remember, delta H reaction is, it's, what did I say it was for you? So it's the delta H over the moles, right? Yeah, so we're just going to divide this number by 1.62. So yes, so we'll technically have our coefficients. We'll find it for 1 mole of carbon dioxide, and then we'll go ahead and expand it out to the full reaction. So what do we get here? Negative can be excluded in the equation. So that depends. So because we never look at the surroundings for bomb calorimeter, we should include the negative. I would include the negative there. Just because we can solve for Q reaction directly, just a little bit easier on us. So I would keep the negative there. Okay, and so looking at this, it looks like we got kilojoules per mole CO2. So I didn't want to make this one tricky for you guys, but I accidentally made it tricky for you guys. I'm sorry. You're probably asking, why is it tricky? Because so this number here tells us we have that, right? That is what the yeah, exactly. We'll cover everything. So yeah. So if we want it for 6 moles of CO2, we would need to multiply this by 6, right? I just wrote 87. I didn't write times 6. I'll show you what this is gonna look like. So what we have done, what this number is for this reaction. Because the coefficient that we've solved for is 1. Let me just go ahead and erase the 522 for now. I guess I should write 1 there, but so again, I did not mean for this one to be tricky in this regard, but sometimes that happens when I just make up problems on the spot. So I mean, this would be totally okay. Like if this were your reaction, you could use this, that you'd be done. But the reaction given was 6 CO2 plus 6 waters turns into glucose plus O2. So technically, the delta H for this reaction was 87. The delta H for this reaction is 6 times that. So I'm sorry, I did not mean for this to be the problem like that, but hopefully this part makes sense. Like, I'm not going to try and mess with you on your exam like this. Again, that was beyond... Where the hell is my phone? Let's see. Oh, I hear it buzzing. Oh, well. It's probably the dean calling me saying I'm late to some meeting or something, but oh well. That's okay. Yeah, but... Yeah, exactly. It's all just steps and formulas. That's all it is. So, I can maybe try and find more practice problems for you Ones that have like we did with the oxidation numbers and all that stuff. I found like all this extra practice for you. I can try and find thermochem ones so you can just practice more and have the answers already for you. So you can just do as much as you need to feel comfortable with it. So, yeah, the math is not hard. It's just figuring out what the heck to do with these numbers. So, yeah. Exciting. Fun weekend ahead indeed. um, yeah. So, we have to remember here's a formula we used. Here's technically a formula we used. We had two potential formulas that we used one of them. Yeah, we had a lot going on in this problem too. And I understand it's not so easy to figure out all of this stuff. How are we with like the Hess's? Oh my gosh, we have homework problems to do. Okay, let me do those first, and then we'll get back to more questions. So we had question 66. Okay, we can do this one. So this one is a Hess's Law problem. Just copying the question here so we have it for easy access. And we have N2O turns into 2N2 plus O2 delta H is negative 163.2. Okay. Awesome. Oh, I guess I should once again tell us what the actual question is asking. We're asked to calculate delta H for okay. So what we're looking at in this problem, just like before, or rather not just like before, we are trying to get these three equations that were given to add up so that they form this last equation. Oh, I see. Yeah, we could totally do that. That would work. I like your idea. That should be nice. That could work for us. So why do we need the first equation then? Let's see. It's making NO to make NO2. Oh, I see. Okay. Yeah, that could totally work. You could multiply by a fraction, no problem. That would work totally. So you have identified that yes, we are going to need the NO2 to be reversed, right? But also like multiplied by different numbers, right? Yeah, you would be multiplied by 3/2 rather. Yeah, that's okay. Yeah, I totally get it. Yeah, because we need 3 NOs. Yeah, for sure. So walk us through it. What did you do otherwise? So I like your idea that you said we had to do 3/2 for this one. So what else are we going to need to do here? I like it. That would work. And number 3 divided by 2. Plus minus. Yeah, for sure. So, and then the last one you divide by 2, right? So, in fact, all of these we are using fractions, right? Yeah, exactly. So, switch in half. Perfect. So, it looks like you had it all right. Yeah, you can totally use fractions on these. There's no problem there. So, the total delta H, if we add all these up now that we've done our things, should be negative half times delta H2 plus half times delta H3. Did we have to reverse that one? No. Okay. And so that becomes 3 halves times 180.7. This one we're going to flip, so it's going to become plus 1 half times 113.1 plus, rather subtract, so we do all this fun stuff, and yeah, this is totally okay. So yeah, I guess in class we had done mostly like multiplying ones, but yeah, sometimes you will have to divide instead. So fractions are totally okay. There's no problem there. So doing this math, you get whatever your answer is. I don't want to do the math, but that's how you would do it. So yeah, you are totally right. 3 halves will work. Okay, so Kevin, which question did you have again? Was it 62B? I could scroll up and find out. 62B. Okay, yeah, we can do that. Okay, cool. So I'll let you. Does anybody have any questions on this one? This was number 66. Okay, well, let's just do 62B. So 62B is saying we have 2 reactions. Oh gosh, enthalpy diagram. Okay. Yikes. Okay. I assigned this one to you guys, really? Oh well. We can do it. So we're given A to B is delta H equals plus 30. B to C, delta H equals plus 60 kilojoules. Okay. Part A had us calculate for A to C, and which would be 90, right? You just add them together. Right. So part B is asking for an enthalpy diagram to show how this works. So we see that overall we kind of have 2 sections here. What? Okay. We know that C is our highest energy because each time we go in this reaction, go to A to B, we have to put energy in. It's endothermic. To go from B to C, we have to put energy in again. So it's also endothermic. So we know that C has more energy overall than A does. And we see that B is going to be somewhere in the middle, right? Why did I draw it to the side? So, I mean, this is delta H going up. So, like, let's say A started at 100 kilojoules, then C would be 190 kilojoules, right? It's just the difference between them. So, we saw that to go from A to B, was 30 kilojoules. To go from B to C was 60 kilojoules. Or to go from A to C directly is going to be 90 kilojoules. So this is what your diagram would look like. It's just as simple as that. And so to show that Hess's law applies, you would say, okay, well, 90 equals 30 plus 60. Yay. Good. I didn't mean to assign you this problem because I don't think there's that much to be gained from making you do it visually. Yeah, this is all it is. So it's nothing crazy. So that's just what the diagram would look like if you were to draw one. Okay, so you're just kind of like double checking, really? That's what you wanted to do with that? Okay, cool. Then, yes, that's that. Okay, I might have time for one last question if it's quick. I have a ping on Discord. Let's see if that's from one of you. It's from the 101 students, so we can ignore them. We don't care about the one. Yeah, I know. Okay, yeah, so in exothermic one, you would go down instead of up. So, because just typically it's just, if you're going down, that's showing you're releasing energy, you have less energy than you had before. If it's endothermic, it's going up. I haven't written it yet. What do you mean, though? I mean, I planned for it to be about half and half, so half would be solution chemistry, half would be thermochemistry. Still going to be multiple choice, unless there is a mass uproar. I don't know yet. So how it works is I'll basically like make a test real quick. I will take it, see how long it takes me, and usually I'll give you either 3 or 4 times as long. And so I usually shoot for about 75 minutes or so. So I'm looking for one that takes me between 20 and 25 minutes to do. And so it's however many questions that happens to be. So, yeah, so more time limit, huh? You want me to do 4 times instead? You want 100 minutes? Maybe. Maybe for this one because it's thermochem. But that means I could give you harder problems. Alright, that's the deal we'll make. 5 times as long. Just keep adding more and more. Alright, it'll be 100 questions and you can have all day. Have fun. Well, I mean, there's no way I could... I mean, something like this, like 62A, that would be a problem that you would do in all of, 10 seconds? Like, that one is a joke of a problem. But something like this one would take you quite a bit more time, right? There's going to be a mix of them. And so, as a result, like, this one would be worth more points because it is longer. Yeah, that would be nice. Yeah, I think I know how to do that, Melissa. I can try to do that. What? Burn the school down? No, we're not going to burn the school down. Yeah, I know what you're saying. Yeah. Oh, I can do that. I hope. Canvas can be fickle sometimes, but I should be able to do that. Let's see, anything else on that? I don't have anything. Okay, so yeah, that's I will consider how long it's gonna be. I will let you know once I have written it, but that might not be till like Saturday, maybe Sunday, maybe Monday morning. No, I can't do Monday morning because it comes out at midnight, right? So, yeah. Okay, well, with that vocab type questions, maybe those would be easy questions for me to do. I mean, I don't like to give definitions because this is easy to type in Google, like, what's work? And, they could, that's boring. I'd rather you apply the definition rather than just spit it back out at me, so. But, like, some of the work calculations are easy, like P delta V, like, 2 minutes, easy, done. Okay, well, with that, I have a meeting to go to, though it should have been at 11:30, so I hope that wasn't the dean yelling at me that I'm late. So, yeah, just do all easy problems, just all work problems. Okay. Alrighty, so I'll put these up. Don't mix the problem, get thermal through. I usually don't mix the problems. So, usually they're in groups by category. So, like, all the, solution conceptual questions would be together, and then the solution calculations would be together. I usually do it that way. That's the easiest way for me to do it as well. So I know exactly, okay, I want to give you 6 questions on conceptual, whatever, blah, blah, blah. So yeah, that'll be okay. Alrighty. See you guys on Tuesday. Though I'm sure I will be answering your stuff Sunday at 5 p.m., or whatever. So, cool. See you guys then. We'll finish off our electron configurations, and then we'll move on to whatever the heck is next for us. Lewis structures, maybe. Okie doke. Take care.